the total energy of the universe is exactly equal to zero. And Steve Hawking was there. It consists of many different pieces which do not talk to each other. Do you think that this carbon-type life was a necessary intermediate step in the existence of life?
Hi, I'm Greg Mustreader, and this is my podcast on rationality, transhumanism, and trends of development in society. Today, here with me is Andrei Linde, a Stanford professor and the founding father of the inflationary theory of the universe. Hi, Andrei.
Hi, how are you?
Great, thank you. Welcome to the podcast. The first question that arises for most of our viewers who have not watched your lectures, I have, and I have been mind blown, but most people haven't. So please explain for them in brief, in a couple of sentences, what the inflationary theory of the universe is about.
Okay, this is something similar to kind of magic trick. In the standard Big Bang theory, you needed to start with the same amount of particles which we have right now in the universe. In the universe right now, it is approximately 10 to the degree 90 particles, which is 1 billion of a billion of a billion of a billion of a billion. Okay, you got the idea. The total mass is about 10 to the 50 tons. So this is a huge baby. Now, according to the Big Bang theory, all of this universe was previously tiny, like 1 centimeter or smaller. And then suddenly it all started expanding. And when it was smaller, its total energy was actually much higher because it gave later part of its energy away when expanding. So the first question, who gave to the universe all of this energy? Because how it is, you have no money in the pocket and in the morning you have a billion. So nothing like that happens in real time, right? All of these processes which started the universe, they all started simultaneously. And it was, okay, so why not? This was the beginning, right? But here's a problem. If I am looking right now to the right of me and to the left of me, I can see to the right of me at a distance which is the age of the universe multiplied by speed of light. That's how far the signal goes. So I see at this distance.
To the visible universe, right?
Visible universe, right? Yes. So what I can say is that the universe is bigger than what I see. And how far I see is this 10 billion years, actually 14 billion years multiplied by speed of light. Actually, it's a little bit more than that, some coefficient 2 or 3 depending. Because what I see right now is actually at the moment is further away because the universe was expanding. I see the objects which are just slightly greater distance of me than the speed of light multiplied by the age of the universe. Now I see what is to the left. I see what is to the right, whatever the sides are. And then the left galaxies, people who live far away of me at this 10 billion light years away, they see me, but they do not see what is to the right of me. Because for that, they would need to have another 10 billion years to wait. So what happens is that the universe right now, already at this time, it consists of many different pieces which do not talk to each other. And if I believe in the theory of the Big Bang, then at the beginning of the universe, in this tiny object like 1 centimeter, there were about 10 to the 90 different regions which did not talk to each other, did not know that other parts of the universe exist. So then the question is, how did they know that it's time for them to expand? Because I do not know how my neighbor lives. I cannot say, hello, it's time to expand. So that's the problem. It's called horizon problem. Why our universe is homogeneous? Because right now, density to the right of me and to the left of me, density of the universe at this large scale is almost equal to each other. It's to the right and to the left, they have the same average density with accuracy better than 1 in 10,000. So who polished the universe? And was it possible to polish the universe when your right hand does not know what the left hand is doing? Okay, so that is one of these issues. Why our universe does not rotate? Like our sun, our planet rotates about the sun. Our sun rotates about the center of galaxy. Our galaxy rotates as a whole. Our universe does not rotate. What's wrong with it? Why our universe does not rotate? Why up and right and left, whatever, all of these directions approximately equal to each other? It's called isotropic. So there are some strange things about our universe which we could not understand in the context of the Big Bang theory. And inflation came with a simple and magic idea, and this idea was first proposed by Alan Guth. Let's just start it and let it grow exponentially fast, being in a vacuum-like state without any particles at all. Sounds crazy. In the vacuum there are no particles, I understand, but then vacuum doesn't have any tendency to expand. Well, in the theory of elementary particles, it's possible for vacuum to be very energetic. There are some fields which are called scalar fields, which look, if they are uniform, if they do not move, they look like vacuum state. You go through it, you don't notice it, but it may have very large energy density. And then it may decay. And if it decays, then this energy goes to energy of particles. So particles can be created by the decay of vacuum state. Suppose you have 1 cubic meter filled with candies. So you have 1,000 candies in 1 cubic meter. Now expand it 10 times. It's the same 1,000 candies inside, but the volume have grown 1,000 times. So you will have only 1 candy per cubic meter now. It's the same 1,000, but the volume have grown 1,000 times. So in 1 cubic meter, you have 1 candy. Instead of that, the idea is this. You have this 1 cubic meter filled with heavy vacuum. Then this heavy vacuum exponentially grows. After some stage, it becomes 1,000 times greater than its original volume. Okay? And then the vacuum decays. So the energy density inside the box is the same. It's nothing. It's vacuum. Vacuum did not change until it decays. So the energy density is the same. Box have grown 1,000 times. The total energy is energy density multiplied by volume. It became 1,000 times more. Sounds like cheating. Sounds like magic trick. We know that energy does not appear from nowhere because the total energy of the universe is exactly equal to 0. This is the sum of energy of elementary particles plus energy of gravity. So when the universe expands in this vacuum-like state, energy of matter grows exponentially, whereas energy of gravity becomes exponentially large but negative. So in total, everything is fine, but you have a kind of strange instability where you can pump energy from gravity, make it energy of matter. And then this vacuum decays and it produces these candies. So now the total amount of candies, the total amount of protons, electrons, whatever particles from which we are built, becomes proportional to the total volume of the universe. So if this stage of exponential growth was long enough, then you produce exponentially large number of particles. So you have a possibility to explain why you can start from practically nothing and then you get everything. And then while the universe was exponentially expanding, suppose it starts with some uneven shaped universe, like very nasty looking universe. And then it expands, it grows. And when it grows, all of these inhomogeneities are stretching away. So what was previously very inhomogeneous thing, it continue being like, say you have an apple. An apple is not really spherical. But if you live on the surface of an apple, then when the apple expanded, you live on a tiny, tiny part of this surface and it looks completely flat and very, very homogeneous. So that's the trick. The trick is that you do not change the shape of the universe, but you make it so large that you do not care about its shape. You just look at tiny part of the surface, which is stretched, which becomes homogeneous and flat. So that was a great idea. And it would be great if it worked. So this was what Alan Guth called inflationary cosmology, inflationary universe. Unfortunately, in the end of his own paper, he have written, sorry guys, there is a little bit of a problem. And this little bit is that this decay of vacuum, which is necessary for produce matter, this decay of vacuum looks like boiling of water. Boiling of water appears one bubble here, one bubble here, one bubble here, okay. So in boiling universe, these bubbles collide. And the universe becomes very messy, extremely inhomogeneous. All these advantages of the theory go away because you produce total mess. So here is this. What do you do about that? And for about a year, more than that, all of us were working on it. And eventually there were two papers, one by Alan Guth, together with Eric Weinberg, and another by Stephen Hawking, together with some collaborators, essentially saying that this idea is dead, it's impossible to improve it. And thanks God, mail from US and UK worked very badly in the direction of Russia. So I received this preprints after I already improved it. So there was necessary to make this transition from one vacuum to another, make it kind of gradual, so that you do not have this well-defined bubble. So here you have red and here you have white. And so instead of that, you may have it like you have white, and then it kind of become pinkish a little bit more, and then gradually have red, and then you have particles forming. And in that case, there is no colliding bubble walls. Everything ends up normally. Universe just stretches and everything is fine. So I called this theory new inflationary scenario. And it worked nicely, almost, because when I gave a talk about it, at first I gave this talk at some international conference in October 81 in Moscow, and Steve Hawking was there. And next day I was invited to translate his talk in Moscow University. And usually Steve would prepare for his lecture in such a way that his students would give a lecture and Steve just correct him a little bit and it would be easy for me to translate. But this time they did not prepare. So Steve say something very difficult to understand. Then his students say one word, and then I translate this word. But then in the end, I understood what they're talking about. They were talking about inflationary cosmology, why it is impossible to make it work. So I start, instead of translating one word, I start giving a talk, essentially. So I was explaining why it is impossible to improve it. So everything was smoothly for half an hour. And then in the end of this half an hour, Steve said, and recently there was a very interesting suggestion how to solve this problem by Andrei Linde, and I happily translated. And then he said, but this suggestion is totally wrong. And I translated. And for half an hour, I was explaining everyone that my theory, which I first reported yesterday, that it is impossible to make it work. It was not fun at all. I've never been in a more stupid situation in my life, I think. When the talk was over, I said I translated, but I disagree. And do you want me to explain what is going on? He say, "Vava." His students say yes. And then we rolled to some room, discussed, and then discussed, and then discussed. And then he told me, but you didn't tell this before. And whatever this repeated. And then he invited me to his hotel. And then he started photographing me, showing me photographs of his family. And we became friends. So this was the beginning of new inflation. But one thing was right in the end, that this theory survived only for 1 year. Because quantum fluctuations destroy homogeneity of this otherwise perfect universe. And I invented another scenario, which was called chaotic inflation. Alexei Starobinsky in Moscow, in fact, invented the scenario in 1980 which was not originally called inflationary theory because his purpose was different. But it's actually happened to be also a totally consistent version of inflationary theory. So inflationary theory started from that. So to summarize, the idea is take initially empty universe. You can take it as small as you want. You can make it in the beginning as empty as you want, except for it must have some piece of space filled with this energetic vacuum. And then let it expand and let this energetic vacuum give energy to normal particles. And after that, you get the universe, which is homogeneous, huge, has lots of particles around, and it does not rotate. Why it does not rotate? I remember this story about where you can see it on this skating, when the ballerina rotates and then she spreads her arms and rotates and ceases to exist. So the universe, because of this rapid expansion, have spread its arms and it stopped rotating because of these fast spreading arms. So you have with one relatively simple idea. I mean, it's really, if you write equations, it's very, very simple. It's very difficult to understand what is going on. It looks impossible, contradicting many rules which we have. But then if you study it, nope, it does not seem contradicting. It seems everything is all right. So using this simple idea, you suddenly can explain simultaneously many, many different things about the universe, which we couldn't explain otherwise. So that's the basic idea.
Oh, wow, let's take a step back. So first of all, a great analogy with the apple. So we are like bacteria on the surface of a huge apple that has been stretched. That's why we see it as a straight surface, because it's huge and we don't know that it's curvy and that it has different shape. That's good that you visualize and you understand. But I didn't get how you get from vacuum to particles. So the fact that vacuum has energy, does this fact produce the particle?
This fact allows particle production. But the mechanism by itself is the following. You have this scalar field, and I said that it looks almost like a vacuum if it does not move, if it is uniform. So expansion of the universe makes it uniform, but it cannot stop it moving. If it was in an energetically disfavorable state, and then it starts falling down, then it starts moving. So once it starts moving, it comes to the new vacuum, and it starts oscillating back and forth near this vacuum. And oscillating fields, they can produce elementary particles. They stop oscillating, giving energy to energy of normal particles. This is not an easy story. It is all requires knowledge of quantum field theory in curved space. But once you know the general principle, then it's no more complicated than any other quantum field theory. I mean, some things about inflation, they seem crazy, okay? But if you look at any particular part, calculations which require to check how the theory works, they are not crazy. In each particular step, you just check that what you're doing is right using regular methods of classical field theory, quantum field theory, general relativity.
So you came up with this theory and improved it in the 1980s with your colleagues, right?
Mostly, but I continued doing it as well as many other people, because after it became clear that you can make the theory work, there are lots and lots of other people involved. And in fact, even before we formulated the inflation theory in the way how it is, in Moscow, in the same institute with me, Lebedev Physical Institute, there were a couple of people, Mukhanov and Chibisov, who studied quantum fluctuations in Starobinsky model, which, as I said, was one of the versions of inflationary cosmology. Okay, and they found that quantum fluctuations during inflation, when the universe is stretched, you take small fluctuation of small size, it becomes long wave. because the universe stretched it, large size fluctuation. But during this process, the amplitude of fluctuations does not change during the stretching. It's a tricky effect. Then other quantum fluctuations add up to this, and all of them together, they form new inhomogeneities in the universe. So you start with whatever inhomogeneous, whatever non-uniform universe, then you stretch it, it becomes classically, at the classical level, it becomes extremely homogeneous, 100% homogeneous. But then quantum effects produce tiny inhomogeneities. And the theory of these inhomogeneities was studied starting from this paper by Mukhanov and Chibisov in 81. And then in 82, there were a group of people in the UK, in the United States, also including Alan Guth and Steve Hawking, others, who developed this theory, and this development goes right now, which says the following: when you make the universe so homogeneous, it's great, it's beautiful, but where are the galaxies? You need to have galaxies. So either they should pre-exist, so then the universe is inhomogeneous and you see this inhomogeneities after inflation, or you create the galaxies somehow. So this strange mechanism of creation of quantum fluctuations tells you that galaxies are children of quantum fluctuations. You have homogeneous universe, you produce quantum fluctuations, you stretch them, you add new, stretch them, and all of this configuration becomes not a very strong but still sufficient in homogeneity for galaxies to start growing at this place. So galaxies have been produced by quantum fluctuations. And then in addition to that, when you look at the sky and you see that sky doesn't have the same temperature in all directions. In this direction, temperature of the sky, this is cosmic microwave background radiation, temperature of the sky is 2.7 Kelvin. Very, very tiny. When I'm talking about temperature of the sky, is that when these particles were produced after inflation, they collided with each other and the universe became hot. So it was like Big Bang, but after inflation. And then when the universe expanded, this temperature drops down and it became approximately 2.7 Kelvin, which is really, really non-energetic. It's almost kind of radio waves. So what we see is from all parts of the sky, we receive these particles corresponding to radiation with very small temperature, 2.7 Kelvin. But then when people start looking at it with great precision, they found that it is 2.7 plus minus 1 divided by 100,000. Almost impossible to observe, but these guys, experimentalists, they are unbelievable. So satellites mapping the sky, this WMAP, this is Planck satellite recently, but before that COBE satellite, people got Nobel Prizes for COBE satellite, finding these fluctuations. And these fluctuations, you see them like slightly different energy coming from different parts of the sky, and you want to know explanation, and explanation is the same inflationary perturbations we are responsible for galaxies. So you get all of this experimental data bringing different consequences of inflationary theory together, and people check whether it matches inflationary theory, and basically it does. Okay, we used to think that quantum is quantum. It's something tiny. It's for like structure of atoms, maybe. But quantum fluctuations during inflation produce galaxies. So this is as insane as it possible that we live inside a galaxy, we are much smaller than a galaxy. So how can I think that I am a grandchild of a big quantum fluctuation in the early universe? And that's one of these parts. And then when you study the theory, makes sense, people checked each other many, many times, calculations and everything. And they all agree that, calculation is fine, but the result is crazy. But so sorry, this is what we see on the sky. So nobody knows, of course, for sure, but it looks like there's a very good chance that the theory is just right. despite the fact that it predicts these strangest possible things.
Is there currently scientific consensus around the inflationary theory? Is this like the mainstream theory?
Well, it's always difficult to make a generic statement about that. But just to give you a practical example, which is sociology maybe, the Planck satellite, which is the most advanced satellite studying cosmic microwave background radiation, the most famous experiment, $1 billion. Okay, lots of people in Europe, in different countries, working to check this cosmic microwave background radiation. They have written several different papers comparing the data with experimental data, and in particular, to explain it, to explain what we see, they compared it with predictions for different theories. So in the beginning, they compared it with inflation, and then maybe a little bit of cosmic strings, maybe some alternative models, etc. In the latest data releases, they mention an alternative theory in one sentence, and everything else is about which inflationary theory describes it better. Once again, this does not prove that this is what we are going to live with 20 years from now. Maybe people will invent something smarter, and people are trying, and sometimes they claim that we already did it. So we will see. I'm happy about what is going on there. Let's see, let's wait.
Yeah. So the current scientific advancements prove, or at least give some further ground to that theory, right?
Yes, that's what I see.
Okay, so another topic that arises out of this is the idea that we live, in fact, not in a universe, but in a multiverse. Can you please explain how this follows from your theory?
So suppose your universe is, a red universe, which is of uneven shape, whatever, and then it all expands exponentially. And it continues being red, it just becomes locally very homogeneous and uniform, which is what inflation does. But what if you start with a universe which is like a football? One part is white and then black, white, black, white, black, okay, like a normal football. Then when it expands exponentially, white part becomes exponentially large and white. Black part becomes exponentially large and black. So you have a set of different parts of the universe with different properties. And the guy who lives on the white part, he will look around and say, oh, the universe is white, because I do not see any other types, because black part of the universe is exponentially far away, so I don't see it. So our universe must be white. I don't know why it must be white, but I must construct a theory which explains why the universe must be white. And the guy living in a black universe will look around and say, yeah, our universe is black. I know it because everywhere I see it's only black. So I must construct a theory which would explain why the universe must be black. Now imagine that instead of the two-color football, you have multicolored football. Black, white, yellow, green, violet, whatever. And then each part of it expands exponentially, and you get different universes, which are black, white, yellow, green, violet, different colors. Yeah. Then you have different universes, so to say, which do not talk to each other because it's not that they are far away from each other, they are boundary between them. But the white area is so large that people living there, they don't know anything about the red ones. And each of them will try to explain why the universe must be the way it is, because this is the main goal of science, right? Okay, we want to explain what is happening with us. And there is another possibility that you can live in white, you can live in red, and it's just where you have been born. It's just like if the China would be exponentially large, okay, and Russia exponentially large, then Russians will never know about Chinese. They have their laws. In Russia, they have their laws. In the US, they have their laws. And each of them will try to explain why our laws are the only ones which are possible and right, and everything must be just exactly like it is here. But there is this different perspective, which I called cosmopolitan perspective. That's what really may happen in the universe. Of course, it may happen only if you can have a reasonable theory which would predict it. If you have this scalar field, and the scalar field falls from its unstable state to some stable vacuum, the question is whether this stable vacuum is only of one type or there could be many. We know that in fact it can be many, but before going there, just one simple example from chemistry. You have water. Water is H2O, right? So you have water, but water can be solid, can be liquid, it can be gas. Same water, same chemistry, but different properties. People call them different phases, okay? You have different phase of water. Now, suppose that you are a captain of a ship on this sea, and you see all your life only liquid water. Then you'll be happy, and you will not think about the possibility to crash into the iceberg. So this is better perhaps to know what is actually possible within the same theory. It is not something crazy. It is not something obnoxious, super invented by somebody. But just this simple example shows you what is possible. Suppose you have electromagnetic theory. Electromagnetic theory describes light with all different colors. Green, yellow, whatever color it is. If you know that the same theory, just saying electromagnetic theory, does not mean that you know the color. You have electromagnetic theory with green light, with red light, you know it. You drive the car, you know. Okay, so this, in translation to what we know about the vacua, there is a theory which nobody knows whether this is really the theory of everything, but this is an interesting candidate which people study for many years. It's called string theory. Long ago, when people started developing this theory, they kind of complained that in this theory there are too many vacua. Not that they really constructed all of them, because it was really very complicated, but they have seen that the conditions for constructing pretty broad, and you usually have lots of them. So when I have this vision of this multicolored universe, I said, look, this is not a disadvantage, this is an advantage, because then you have all of these different laws of physics corresponding to different vacua. In different vacua, properties of elementary particles may be different. Then you have this huge number of different vacua, and depending on which vacuum you happen to be born, then you have different laws of physics describing these parts of the universe. And if there are many, then it's just good, because you do not need to explain everything that you see. However, there is one thing which is a property of all of this vacua where you can live, and that is that you can live there. You would not even try to explain why I live in the vacuum where I cannot live. No, I make my experiments. This is about the part of the universe where I live, so by definition, I live here, okay? So there is a correlation between my ability of living in the universe of certain color, okay? There is a correlation between me and the universe where I can live. Like dolphins can live in water. I can live only on dry land. Again, there is nothing metaphysical about it. I cannot live, breathe in water. And I cannot live in interstellar space. So there is a correlation between the places where I can live and my own properties. There is nothing wrong about it. Then I'm looking at this multiverse and I say, well, interesting. It's anthropic principle, which I despised and many other people despised for many, many years, because they were saying the universe the way it is because God created it the way so that I will be able to exist there. And Hawking used to joke, I wouldn't believe the God created the universe for a benefit of this particular type of monkey. So what happens in this multiverse theory is that the universe, eternally producing itself in all of its different copies, all of different colors corresponding to different laws of physics, working in different parts of it. And then when we look at different parts, we say, in this one I cannot live, in this one I cannot live, this one where I can live, what kind of properties it must obey. Like, for example, study mass of the proton and mass of the neutron. We know that mass of the proton almost coincides with the mass of the neutron. If mass of the proton would be 1% heavier, then all protons will decay into neutrons and our universe would consist only from neutron stars. If a neutron would be 1% heavier than proton, then there will be no complicated nuclei, only hydrogen. So the universe would have only hydrogen. We cannot live in the universe like that. So now I say, I have lots of different vacuum state and string theory. In some of them, neutrons are heavier than protons. In some of them, protons are heavier than neutrons. But I cannot live in these universes. I can live in this one. That explains why the masses of neutron and proton are so close to each other. Interesting. Let's check about the electron. The mass of the electron is 2,000 times lighter than the mass of the proton. Why? 2,000 times. Who gave this number? Well, if it were 10 times heavier or 10 times lighter, we would be unable to live in this universe. Interesting. So coincidence. Vacuum energy. Vacuum energy in general, it can be humongously large, extremely large, maybe even negative. If vacuum energy is negative, the universe is like that, they are very quickly collapse. If vacuum energy is large and positive, then the universe expands so fast that it tears everything apart, galaxies would not form. So I can live in the universe where the vacuum energy is very tiny. Let's check what experiment gives us. For many, many years, people tried to prove that vacuum energy must be zero. They could not do it. Then experimentally, they found that vacuum energy is really extraordinarily small. But if it were 1,000 times more than that, then galaxies would not form. So here we know the explanation, or possible explanation, of why vacuum energy is so small. And to make sense out of this explanation, you really need to have something like multiverse. Because otherwise,
So because there is an infinitesimal number of these universes where life would not be possible, protons would not form, or vacuum would not have energy, right?
Because there are a large number of universes of all types. The ones where we cannot live and the ones where we can live. And in fact, of course, I would guess that the number of the universe where we can live is much smaller. Okay? So you just have a subset of all possibilities. In essence, this is something which Murray Gell-Mann called environmental principle. There are some properties of physics which are fundamental. Like you have some fundamental laws, like law of gravity, whatever. Okay, and there are some parameters of the theory which may or may not have any fundamental explanation. And that is similar to what I told you about water and ice. Both are possible. It's just temperature in one part was smaller and then the water was frozen. Okay, so what you may have indeed the universe with different coupling constants, with different masses in different parts of the universe. And you try to find an explanation to all of these constants. And for some, there are some relations between them, and then you won a big game. Yeah, that's great. If you can have explanation, scientific, full explanation, without using anthropic principle, then it's fantastic. This is what all of us want to do. But sometimes, how much you try, you cannot find this explanation, and actually the parameters are totally ugly. very strange, random looking, etc. And there are only one non-random part about them, that if they would be considerably different, then we would be unable to live in the universe where we could measure these parameters. So this is a strange way of thinking about the world. And if we would not have this option to have a universe of this type and the universe of that type, then this way of thinking would be meaningless. So what I'm trying to say is something kind of tricky, because many people who do not like the theory of multiverse, they say that it is typical metaphysics, etc. Just think about it. If you live in the white universe and this exponentially large, and you never see a black universe, then saying that the black universe may exist looks like metaphysics to you. You will never prove it, and this violates some of the basic principles of physics. You must have reproducible results of experiments. You must verify everything, and only after that you have a theory which you can trust. If you do not have any experimental evidence in favor of existence of the black universe, and you just speculate about it, it's just like speculating about the life after death, etc., until you have reliable evidence of that. Well, who knows? Maybe we have, but maybe we don't, so then we can argue. But about this black universe, by construction, it's exponentially far away from us. So do we have any experimental evidence in favor of it? And here I say something which may be a little bit strange sounding. We have this experimental evidence because we have many experimental data, like smallness of the cosmological constant, and coincidence between proton and neutron mass, and the smallness of the electron mass, and particular value of the electron charge. If you change it several times, life as we know it would be impossible. And the only way to explain many anthropic coincidences is to assume that the universe is a multiverse, that you have this choice. If you do not have this choice, then the experimental data are unexplained. So, anyway, this means that you have experiments, you have experimental data, and this experimental data have explanation only if you assume that the multiverse exists.
Or if you assume that we are just incredibly lucky to have all those factors.
This is also right. And there is also a possibility that our universe is created with a particular set of laws, and only the devices of a special type which have computational abilities have been created there. So maybe we should start from the different end of the problem. Maybe we should start at saying that the laws is fixed, and life by itself, well, it just appears only if it is possible. And if, for example, there were no weak and strong interactions, life as some way of information processing would be possible in completely different form. This is something which is not entirely stupid, looks a little bit strange, but that is one part of science which we must take increasingly seriously. We know that there is a correlation between our properties and the properties of the universe where we live. So we try to go both ways. What could be if we were different, and what could be if the multiverse is different? And I guess only if we take both these options into account, then we have a better chance to explain everything that we see. Sometimes I have this vision of a conference hall populated by robots 100 years from now, and they are involved in a very complicated discussion. Do you think that this carbon-type life was a necessary intermediate step in the existence of life, or it was actually inevitable? And so this will be a scientific problem for them. So we are kind of anthropically centered in a sense. We think that this is our life and that is a life. Okay, and it is not necessary to think this way. I'm just saying that there are many things which are really demonstrably crazy. Sometimes we are receiving letters from, well, sometimes, every week, almost every day. I am receiving letters from people who suggest alternative explanations of everything that we see around. And the problem with this is usually people do not know really science, and they suggest something which is not even wrong. But on the other hand, if you stop allowing yourself a little bit of freedom just to go slightly out, study different ways of asking the same questions, or study different questions to be asked. Before creation of inflationary cosmology, nobody really was focused on explaining why the universe is so large. We just knew that the universe is large. So asking the question why the universe is large is meaningless. Here is a universe. This is big. Okay. Now, when we learned that inflation can explain why it is big, then you stop thinking about it like a meaningless question. And then you ask another question, why the universe is uniform? And then step after step after step, these meaningless questions happen to have one relatively simple answer. And then this answer, in addition to the answer to these questions, also explains some properties of our world which we did not know exist, like this spectrum of cosmic microwave background radiation founded by COBE and then Planck satellite. So new experimental data. And this new experimental data we are not just explaining, but the theory predicts them. And then there is some agreement. So then you see that sometimes asking a little bit crazy questions may be okay. Well, if you know how to answer them.
Do you think that the simulation theory proposed by, I think, the Swedish philosopher Nick Bostrom may be true, may explain all this? The theory that we are all living inside a simulation.
I do not know whether we should say that it's an explanation or whether this is one of these crazy things which are not totally impossible, and definitely he was not the guy who invented it. I remember myself when I was in a nice grade in school in Moscow, and we formed science fiction club, and we were reading some stuff, and I was thinking about science fiction as well. Yeah, that's fiction. And then somebody have read story of Stanislav Lem when Yon Tichy returned back to Earth, and some crazy scientist invited him in his lab. And in his lab there were lots of different boxes standing, and he asks, what do you think the boxes are? Lots of wires going there. And he says, I don't know. Well, these are brains. And I feed them with information from this huge computer which I have here. And how do you know that you see a flower, for example? Your eyes get these signals, which are red and some shape, etc. So I'm sending this brain shape of a flower, and I send them an information of his hands and of his hands having this flower. So I am sending him all information about his environment. In this box, there is a scientist. In this box, this is a beautiful woman. Each morning, she looks at herself, and there is some scar on her shoulder, and all details about all of this. And this scientist, he is crazy. He thinks that God created him, whatever. When I've read this, I was actually absolutely shocked, because it told us that we must question lots of deep issues, study different answers to stupid questions like how do you know that you really exist and not in this black box in a laboratory. It still remains a very interesting question which I study. My response to that at that time was that I immediately realized, I started reading books on philosophy and realized that there is no easy answer to this question among philosophers. I was kind of disappointed, but then I started developing a theory of consciousness because I thought that if I see apple, then actually my understanding that this is a real object comes from my experience. I have a feeling, I see this red. I have this taste. Okay, so taste, I know taste exists. I know sweetness. I know pain exists. I don't know about apple. I don't know about computer, etc. I know that my vision exists. I know my consciousness exists. Everything else is secondary. And I quickly invented a theory of telepathic contact, which allows to explain why mother feels the same as his child. Okay, very, very smart theory. I was really, really proud of myself.
How old were you?
I was in 9th grade, I guess,
Ninth
maybe
grade. Okay.
14, whatever. Okay, but I was proud for about a year. And after that, I realized that in the theory, I relied on the concept of the mother and the child having the same feeling simultaneously. And then I remembered that sometimes, like in the 8th grade, I read something about special theory of relativity, which claimed that the concept of simultaneity is ill-defined, because when you move or when you stay, some things which seem simultaneous are not. And then I realized that my theory had this rotten part in the heart of it. So in order to do something smart, something clever, I must actually study physics. Because if I don't do it, then I would live with my theory of consciousness. I would always believe that I'm a genius, but I would be just a stupid fool simply because I did not learn the rules of the game. So before this part, I wanted to be a physicist. Then this was this strange stage where I realized that consciousness is also important. And then I realized that if I want to say something about that, I need to know physics first. So this is what I'm doing right now. I study universe simply because it's simpler. But I think that the theory of us and consciousness is more interesting and fundamental, but it's more complicated. It would be for other people to do, perhaps. Maybe I will, well, whatever. So that's how it is.
Thank you for such a thought-provoking discussion, Andrei. Thank you to our viewers and listeners for joining in. Support my content with a like and with your subscription. Hit the like and subscribe button on YouTube. Rate my podcast on iTunes and other podcasting services. I'm Greg Mustreader. See you next week.